Thank you for joining me. They do say, don't they? They do say that for live TV, you should never work with animals, children, and new software. Well, I am going to do live with new software because this is quite grown-up software, so I should be okay. And I'm sure if it goes wrong, it'll be me and finger trouble that causes the problem. So here we have a live updating screen on a VNA, and I in fact have two VNAs that I'm going to use this afternoon. Currently I'm using the top one. That screen is a Windows operating system screen, and that is a 106 a VNA 106 on the top and a PicoVNA 108 on the bottom. They are both looking at network metrology training kit boards, very useful boards for demonstrating anything about a VNA, and particularly this new software. So I'm using the network metrology training kits here. And in fact, I've calibrated and I'm measuring already. Not a very clear display at the moment though, so I need to get straight in here and make some adjustments so I can see what's going on. If I click on the parameter at the top right of this plot here, you can see that I can scroll through that quite quickly. I'm using the scroll wheel on the mouse, and likewise let's have a look at this. So on my S11 and S22, I've got a fairly large reflection and some loss along the reflection with increasing frequency. This is a 6 gig span, as you can see. I don't seem to have anything coming through S21 and S12 at the moment. That's more or less noise floor that we see at the bottom there. And that's because this is an open on port 1 and a short on port 2. So not surprising that I don't see any through signal at the moment. Let me add something to the plot here. Let me add axis and change that one to phase. And let's do the same down here. Add axis. And what I'm demonstrating here is that by operating directly on the plots, I can get to the information that I want to see. So I've now got log magnitude and phase for S11 on the top plot, and I've got log magnitude and phase on the top plot, on the bottom plot. I want to see some more detail here, so let's, using the display menu, add some more screens so that I can add some detail here. And we'll change that one to a Smith chart, and this one to a Smith chart. And so already we've got a clearer picture of what's going on, working left to right, S11, S21, S12, and S22. And I've got a total of 8 plots so far. Let's add some more. Let's add a graph at the bottom, and another one, and another one, and another one. Close. And let's get these into the time domain. S21 time domain, S12 time domain, log mag, S22, all in the time domain. And again, if you're familiar with looking at these various plots, you'll be recognizing the TDR response of an open, the TDR response of a short, and still nothing coming through on S21 and S12. Let's change this to a better display here of time. Let's type -1 into there, and what should we do into there? 4 into there, and there we go. So the spans have gone to a new time base now. So I've got what 500 picoseconds per division along the bottom there, and these are, if you like, the equivalent of pulse response type traces that you might get on an oscilloscope. Here I've got 2001 points at the moment. If I click on there, I can quickly change that to 201, and I can see if there's any significant difference. I've lost a lot of test points there, but actually everything there is very little change, so I'm pretty happy with that. Let's see if we can change the IF bandwidth. Yes, indeed we can, and still there doesn't seem to have been much change. So quite quickly, I've set up quite a complicated display. I've got multiple time domain plots. I've got dual axis plots, Smith charts, and I've got all the information in front of me, and I can quickly change the parameters to see that my measurements are all good. Let me switch to workspace 2 because I set all this up earlier on workspace 2. And this is a new workspace. It could be a completely independent set of settings, but actually it's the ones I ended up with there on workspace 1. Let's start that sweep. And let's say I want to save everything to memory. There we go. I've created a memory trace on all of the plots here. The green trace has frozen in time a measurement sweep that we made a moment ago. Now that I've done that, let me change my measurement setup from the short and the open to a completely new setup using the BT line that we have available to us on this board. There we go, and we've got an entirely different plot, and we'll need to make some adjustments here quickly to see what's going on. Okay, and some of these plots are perhaps a little bit cluttered with the memory trace on. I do want to keep the memory trace on some plots, but let me turn that one off, turn that one off. Actually, all I'm doing here is just hiding the memory traces on the top plots, which I can do simply by clicking on their labels at the top of each plot. Okay, well, the network metrology training kit is a PCB whereby the devices that we're testing are in the center of the board, and they are all sitting on equal length feeders, and we don't really want to measure the feeders because, well, for instance here, we just cause a Smith chart to be circling round in circles here. I can't necessarily understand what's going on there. So let's do de-embed, and let's use reference plane shift in this case. We could use multiple networks. In fact, we could use multiple de-embed S-parameter networks. We could use a reference plane offset, and we can use a mix of those. But let me just type in 57 millimeters here. That's the length from the reference plane of the SMA to the dot on the board. And it's the same on both ports. And the dielectric constant is about 3.06. And that's rather changed our plot. our plots. So you can see now that the Smith chart has brought the open round to where, more or less, where we'd expect it to be. We've de-embedded right down to the BT line here. Oh, sorry, the open that we put on as a reference trace. I do beg your pardon. We stored that from the previous settings. That's the open. That's the short. And this is the BT line, all with de-embedded feeders. And I don't know whether you noticed, but when let's just turn embedding off, and you can see that when I turn it off, the time domain plots all shift right. I turn it back on for the live trace, shift left, and I can turn it off for the memory traces, and it shifts right, shifts left. So we can switch on or off the de-embedding that we've applied, and we can do that either to the live traces or to the memory traces. It's a fabulous feature for educating and teaching de-embed. And notice that when I am fully de-embedded, there's a cursor reading there. Look, wherever I hover on this trace, I get cursor readings wherever I go. And if I come to this point here, that is reading off as very nearly 0 nanoseconds there at the bottom of the screen in black. At the bottom of the plot in black, I've got 0 nanoseconds. And that's because I've de-embedded what was a short and de-embedded the BT line impedance here. Okay, workspace 3. And just update this one here. Okay, so on the let's turn off that de-embed page. On the display menu, I can hide all of the memory traces or show them again. Equally, I can delete the memory traces, which I'll do now because I don't need that anymore. I also don't really need these S12 plots because this network is known, it's passive, it's reciprocal. So my S12 plots are exactly the same as my S21 plots. So it's a bit superfluous to have all these up. So let's open the editor. Let's kill these. We don't need those. They're just duplicates. And then let's stretch that across there like that, and that across there like that, and that across there like that. Close. And so I've been able to reconfigure my display quite quickly to have a closer look at things that matter to me and get away from things that really don't. In fact, I'm not really wanting that in the middle anymore. Let's get rid of that one in the middle. And let's make that one a bit bigger. In fact, let's take that one across there. Make that one over there. There. Clear some space in the corner. Okay, so this is my new layout. And I want now to try and understand a little bit more about what's going on in this S11 plot up here. There's some detail going on here, so let's have a look at that. Zoom region. Set the zoom region around part of the plot here. Let's say that part. And then let's add graph, which I'll add there. And so now what I have down here is a zoomed segment that I was looking at up here. In fact, I can edit the segment, bring that trough in there and that trough there, and you can see that my zoomed segment is changing. Let's remove that axis, change that one to a Smith chart, and I don't know whether you can see now, but this Smith is a Smith of the entire sweep, and this is a Smith of my zoom. So I've got complete freedom to play about and get segments and clarify what's going on in a segment here. I can do another one of these. I can, let's do it on this one, add zoom region. Let's home in instead on, whoops, that region, add graph. So I can have multiple zooms. I've got it's a very short one now. Oh, I made that a bit short. A very short Smith here, and I've got another zoom region here, and I can pick as many segments and zoom regions as I wish to. So I could look at multiple channels if I had multiple channel sections in a broadband sweep. Let's add a new workspace and start that sweeping. And this really proves that each workspace has completely independent settings. This is the startup settings for a new workspace. It doesn't have a calibration. So this is rather messy data. It doesn't have any user settings at the moment. Let's close that. Let's load a session. And I'm going to load from the session, the previous session that I've saved, load settings, load data, and load calibration. Open a file. And we'll open that one there. There we go. And so the workspace that I was working towards was this one that I saved earlier, and we can now start that, and it builds as expected. On here, we can add a magnify feature. We can, let's have a look at this Smith chart here. Magnify, and I've generated a little box here. Let's reshape that box, pull it over here, and now what we can see at the bottom of the screen, we've got a very, very large zoom right in on our Smith chart data, which I can read with my cursor, or I can choose to put markers on. So let's use this magnified view, and let's control click, add a marker there, control click. What I'm doing is adding markers as close to the optimum match point, which is the middle of the Smith chart. Add those markers there. So we've got 1, 2, and 3 markers. The readouts are up here now on the right hand side, and you can see that from a Smith chart I've got a readout of megahertz, capacitance, impedance, real impedance, and imaginary impedance, all the data that I might want. What I'm going to do is I'm going to change that marker to a reference marker, and I'm going to group it with 2, 3, and 4 using these tick boxes down here. And as soon as I've done that, we get not only the readouts, the absolute readouts that we had, but we've now got delta readouts, differences from reference marker number 1. And you can also see that I'm presented with a whole bunch of more measurements that I can choose to add. I could add this is on marker 1, I could add log magnitude, phase. So here I'm just adding measurements that I need, just updating there. If things look a little bit slow, that you have to excuse that, because I am running a virtual machine as well, which is taking up more than half of the processor power that I've got available on this poor little i5, which is being thrashed to an inch of its life. But here we go. We can configure all the measurements on our markers without concern for being on the right plot. So I don't need to be on a time domain plot to get an impedance measurement. I don't need to be on a Smith chart to get real and imaginary. All of the measurements are available to me here, whether I'm displaying the relevant plots or not. I can also let's stop the magnify. I can also, on this time domain plot, let's add a marker there and a marker. I'm looking for about the 90% point there. I've added two time domain markers, T1 and T2, roughly speaking, at the 10% and 90% points. Let me change T1 to a reference and group it with marker 2. And now I have the times of marker 1. This one here is 149 picoseconds. Marker 2 is at 759 picoseconds. And the rise time that I'm measuring is 609 picoseconds, the delta between those two points. And in doing that, I've demonstrated that we can do frequency domain and time domain markers, and we are able to group however we wish. The way we group is entirely done by tick boxes. We can have multiple references, and we can have multiple deltas, and all of the data that the VNA has associated with a marker can be displayed numerically. Okay. There we go. And let me bring in this window. Now, here I'm running Linux Mint Cinnamon. I'm running it in a virtual machine, and I will see some lag in this little demonstration. And that is because I'm sharing my screen with a virtual machine. And believe me, that does tend to slow things down on my rather underpowered laptop here. You won't see this lag if you use a virtual machine for Linux and you don't share your screen like I am here. But let's go. Okay. And the first screen or workspace that I want to show you here, let's view full screen. So this is now a Linux screen running exactly the same software, and you might recognize this setup. It's the setup that I had on Windows, because I could open the settings file, the session file, in Linux as well. Or I can do it behind me here. I could do it on Raspberry Pi. So that big TV screen there is running a tiny little Raspberry Pi. There's the box. That's all I can show you of the Raspberry Pi. That's running Linux. And down here on a laptop, this is a MacBook, and I'm running the Mac operating system on that. And all the files that I save with PicoVNA5 are completely interoperable across the operating systems, as they should indeed be. So let's switch over here. This is a fairly big workspace that I'm opening up now, so again it might take a little time. What I'm doing here on the board is I'm measuring the amplifier on the network metrology training kit board, and what I've gathered here for this, let's start the sweep, and I can prove that that is actually sweeping live by placing my finger on the amplifier. So yes, we are gathering live data there. And on a previous occasion, what I've done is gathered a whole set of flatness curves here as memory traces, large number of them, 13 of them, at different drive levels. And so what these are, in fact, are the compression curves for this amplifier, the flatness characteristic at different levels. It's an important measurement that people need to make. And you can see here that I've got a group of markers. They are these over here, 1 to 6, that are on a single point, a single frequency point, in this case 70 megahertz. And then I've got a separate group of markers that are making a flatness measurement here on S12, and I've grouped them separately. So we have the ability to create separate groupings of a great many markers. And in fact, our whole philosophy for designing this software has been not to limit the user. The user could have as many markers as they want. They can have as many memory traces as they want. They can have as many display screens as they want. But ultimately, they're going to run out of monitor resolution, and they're going to run out of size of their plots to see any useful detail. So the limitation in the end is how much display resolution have you got. And on a 4K screen, I've had 32 plots up and still been reasonably able to see and manipulate and add markers and add memory traces and so on and so forth. So very powerful software indeed, software in which we've tried not to limit the user. Oh, and by the way, yes, you can have as many workspaces as you want. You can keep adding those ad infinitum. Okay, so that's a live demonstration of the software. I'm going to now switch to some of my slides just to finish up one or two other points about the software. So let me get that through to next. When we boot up this software, and when you boot up this software, because you can download demonstration copy or download the software, not a demonstration copy, it is the software, and you can download for any of the devices I've mentioned, Linux, macOS, Windows, ARM, Intel, Pi, they're all there available for download. And if you power it up without a device connected, you will get this screen, in which you're able to select demo mode, which will generate some trace data for you and allow you to play with the user interface and understand the user interface and how it works. You can connect to a remote VNA. You could open a file. You could open a file, a session that you'd saved earlier. Supposing you've made some measurements earlier when you were in the lab, you're now at home, you haven't got your VNA. You can open files and work offline here. Or of course you can close the program down. That's the boot up screen. Pictorial, as you can see. More pictures, because pictures are lovely and pictures are easy to understand. This is our calibration wizard, And you may already recognize pictures here of our salt calibration kits. So these are a series of screens that when you do a calibration on PicoVNA5, you are led through these stages, step by step, graphical example of how to make your connections, another one there, another one there, another one there. And each time you've completed the connection, when you press go, a sweep will begin and you get live measurements of your standards. The customers like to see this. It gives confidence that you're progressing with the right standard, that the standard is not damaged, and that you're going to be successful in your calibration. So good to see measurements being made during cal. This little bar here is step-by-step progress through the various steps of the calibration, and you can click any one of those stages on there to go back, to go forward. You can progress the cal in any order that you like, and when you've got all those lit up, all the dots lit up on that bar, you are able to save your data along with a suitable calibration name and information and notes about your setup and perhaps why you did this calibration and what it was being used for. Likewise, there are equivalents if you're using the eCal. Automated eCal is also supported here. Again, right across the operating systems, and here you pick your orientation of eCal and then make your connections and then press go, and these are the progress bars through the whole process. And likewise, there's even a graphical presentation for TRL, TRM calibration. So all those calibrations are available for you on this PicoVNA5, this first release. I've tried to capture here for you, and really the detail of the text you can look at a little bit later, but I've tried to capture here the main selling points, the main features of this ground-up VNA software. It's cross-platform, it's light footprint, it runs on a Pi. Runs on a Pi. Keep going. Screen keeps dying on me. There you go, it's running on a Pi. It's crisp, it's clean, it's snappy presentation and response when you're not doing it on a virtual machine in a webinar. It is anyway. Hover cursor readouts and click to drop markers. So you can drop a marker simply by holding down the control key, hold your mouse over the place you want to drop and click. And there you are, the marker is dropped. You can have single markers, grouped, absolute and delta, and you can have any selection of parameters that you want from your readouts. Most importantly, really, this software has been designed for the automating programmer and for the OE embed opportunities that we see for the VNA. There are two remote programming interfaces. One is a traditional Skippy interface for the GUI, the graphical user interface. So here you would control the VNA through its graphical user interface. Part of Skippy supports local remote interaction, so you can have an automatic program running setups and then an operator interacting with the GUI using the Skippy interface. And of course, the Skippy interface is very common amongst all our competitors. There's a lot of programming, automatic programming material that has already been generated with Skippy-like commands. And here the change to PicoVNA5 is fairly straightforward. There's also a separate EasyBind Programmers API, very powerful API, capable of getting at more functionality than can the GUI. And there will be comprehensive SDK examples for both of those on GitHub. They're not up there yet, but they will be within the next week or so. The whole user interface supports network remoting. Put a VNA on a Pi, connect it on a network, and access it from another place in the world. You can do that. You can mirror the graphical user interface, and as we've seen, SALT, eCal, and TRL calibration wizards. We also have, down in the bottom right-hand corner, there's a feedback key down here. And in there, the user can directly report problems. They can ask for new features. They can prioritize features that are not yet in PicoVNA5, have yet to transfer from PicoVNA3. And so we list those. They're all listed in the feedback forms there, and the customer can prioritize those for us. What do they need to be done most quickly? And that's what we need. We want feedback from you directly to the design team, such that we can move this software forward as quickly as possible and in a customer-driven fashion. These next two screens, I'll leave them to look at for you to look at in detail later if you wish. These help you navigate around the software that I've demonstrated here today, showing you where the features are and giving you clues as to how to access them. There's a slide there for basic interfaces, and then there's a slide here using the examples that I used for the zoom and the magnify features and how to access them. Perhaps the most valuable feature, the workspaces ability. So as I've said before, these workspaces can be completely independent setups. So you can imagine 3-5 students working with the same VNA within a teaching situation, and each of those students would have their own experimental setups on their own workspace. Or an engineer might want different perspectives on the measurements that he or she is making, and those can be all separated out in different workspaces. And you can hold different setups for a test sequence, say. So you could have a test sequence set up on workspace 1, workspace 2, workspace 3, and just work through those. You can even use them to intercompare the effects of different calibrations. So the idea of having multiple workspaces that you can toggle between really quickly, which you've seen me doing, is a very powerful one. So I think if you were to look at PicoVNA3 and PicoVNA5 side by side, that's what you'd see. Transferring from 3 to 5 is a familiar one in that the layouts are very similar, but it's also a very rewarding one in that it is a much cleaner user experience. Controls are where you want them to be, data is where you want it to be, almost nothing is hidden in the menu, and in any case you can get directly at the menus in the bottom right hand corner. So we tried to design such that everything is bang there, right in front of your face when you need it. You don't have to look at that for very long to know where you're going to click to find what you're looking for. The website, on the VNA pages, you'll find there is a new PicoVNA5 software tab. Lots of information on there that I hope you'll find useful. But right at the bottom of the pages within that tab, there is this tabular comparison. There's some titles here. And if you click on each of those titles, then here you see this one's operating system, platform and display. Here are the essential differences between PicoVNA3 and PicoVNA5. And this is all brutally honest. So if we haven't got a feature in 5 yet, we are honest about it and tell the customer everything is listed there so that you can go straight there to see which to use at this point. 3 is still available. It is still fully supported and will continue to be so. We hope, of course, that PicoVNA5 will be much preferred. Now, PicoVNA5 does use the VNA hardware in different ways from PicoVNA3, and older instruments do require an upgrade. Whether it's a 106 or an older 108, if you connect an older unit to the software will identify it as needing an upgrade. And there is a small payment to make for that upgrade. That payment is handled entirely within the application. You can see pricing here. This screen will be presented if you connect an older VNA to the software, and it will ask you to pay for an upgrade to your firmware or to your hardware. You can check this box as to whether you're a commercial customer, a business, or a private individual. And across the world, the Stripe payment system, which is the one we use, is supported in all of these territories. There you are. PicoVNA5 transforms the PicoVNA, perhaps from a little bit behind the pack on the software front. I'm going to argue we're out in the front now. Thank you.